Today on How It's Made. Plastic injection molds. We'll watch them take shape. Automotive oil filters. We'll have all the dirt. Filing cabinets. You can file this one under F for fascinating. And blown glass. We promise you full transparency in this report. If you take a close look at the products around you, you'll notice that many are made of parts that have been assembled together. One way factories make product parts is by melting materials such as metal, rubber, or plastic, then pouring or injecting them into molds. To make a plastic part for a product, the manufacturer has to first commission a mold-making company to design and produce a plastic injection mold. The mold begins as bars of chromium steel, a high-durability metal that can withstand repeated high-pressure injection of plastic. Workers assemble several bars into a block called a mold base. They mount this base on a milling machine, which shaves the bars to the right dimension. This step is critical, enabling them to later machine the base into a mold that's faithful to the technical design, right down to the 100th of a millimeter. A mold usually consists of two halves, each of which is comprised of several components. The factory drills strategically positioned holes in the bases for the guide pins and bushings that hold the components together when the plastic's injected. A grinder now goes to work smoothing and leveling all surfaces. This prepares the base for the high-precision machining operations that will transform it into a mold component. A computer-guided tooling machine called the CNC slowly machines the base, wearing away the steel particle by particle to create the mold component's shape. This one, part of a mold for the plastic rim around a snowmobile's front headlight, takes 20 hours to complete. From here, most mold components go on to a second tooling machine, especially if they have some fine detailing that this CNC machine is incapable of carving. The second machine is outfitted with a copper electrode in the shape of the plastic part, in this case a snowmobile oil gauge. After polishing the electrode to ensure flawless casting, they use a sophisticated measuring device to verify the dimensions. The electrode goes face down on the second tooling machine called the EDM. Directly underneath is the mold half that's already been partially formed on the first machine. A strong electric current runs through the electrode and penetrates the mold, forming a cavity in the shape of the electrode. After tooling, they drill coolant lines. This is for the cooling fluid they'll use to accelerate the hardening of the molten plastic. Some plastic product parts, like that snowmobile oil gauge we saw earlier, have lettering on them. The factory engraves the letters in reverse inside the mold cavity. After the plastic's injected, the writing comes out frontward and raised. The surface of the mold cavity is pretty rough from all that tooling, so they polish it smooth to ensure a proper casting. Here's what the two halves of a finished mold look like. The pins and bushings fit together to close the mold before injecting the hot liquid plastic. Once the plastic cools and hardens, it's just a matter of extracting the molded plastic part. Here's a different molding method. A two-step process they're using to make these buttons that go on the steering handle of a jet ski. First, they mold a structural base out of hard white plastic. Then they put the base into a second mold and inject a rubber-like gray plastic. This softer plastic covers everything but the raised lettering, giving the button a softer feel. Factories also make molds for aluminum injection and rubber injection, among other materials. They build those molds from different types of metal, but using the same techniques. Changing your car's oil filter a couple of times a year is an easy way to prolong the life of your engine. The oil pump forces oil through the filter to the moving parts in the engine. The filter's job is to block dirt and metal debris from getting in between those parts and causing engine damage. They make many oil filter parts from steel coil, a sheet of steel on a roll. They start by unwinding the roll and feeding the coil into a press. The press contains a series of dies, each of which progressively stamps the steel into the shape of the specific part they're making. This press is churning out tapping plates, part of the component on the end of the oil filter that screws onto the car's engine. Hot off the press, the tapping plates travel on a magnetic conveyor to the welding station. There, a robotic arm loads them onto the welding carousel. But before any welding begins, a nozzle applies sealant around the rim of each plate. This is to fill any gaps left between the parts after welding. A robot now welds the tapping plate to another steel part called the bottom ring. This ring will hold the gasket, the rubber seal that prevents oil from leaking out as it travels through the filter into the engine. The welded parts, known as the bottom assembly, now go onto a machine that cuts a thread pattern through the center. This will enable the oil filter to be screwed onto the engine. Another press, meanwhile, produces the oil filter's steel body, called the canister. The dies first stamp out a rough canister shape. Then they reduce the diameter and make the can taller. Then they cut off the excess. Elsewhere in the factory, another machine cuts and perforates pieces of tin-plated steel coil and rolls them into tubes. We'll see where those tubes go shortly. Yet another machine prepares the filter's key component, a filter paper that works like a fine sieve, trapping dirt, carbon, and soot. First, the machine pleats the paper so that it'll fit inside the canister. Next, the machine cuts the continuous ribbon of pleated paper into lengths. Then it folds each piece into a circle, fastening the ends with a steel clip. The next machine assembles what's called the filter cartridge. It places each filter paper over a tube. The tube's job is to reinforce the paper against the force of the oil pumping through it. The next machine glues a capping disc on each end of the filter paper to hold the tube in place. A heater cures the glue. Now for the final assembly. As the canisters go by upside down, automated arms insert the filter cartridges. A worker then puts a thin rubber disc on top of each cartridge. This disc will prevent the oil from draining out of the filter. Now for those bottom assemblies we saw them making earlier. A worker positions one on each canister. Then a machine called a seamer folds its edge down, forming a rim, just like the rim of a soup can. Now the conveyor turns the filters right side up as they file by 5 nozzles spraying powder paint. An infrared oven dries the paint in about 90 seconds. Then a printing machine stamps on the product information. The conveyor now turns the filters upside down again as they travel to the gasket inserter. Its automated plungers insert a gasket into each bottom ring. These automotive oil filters are finally finished and ready to do the dirty work. Whether you work in a sprawling corporate office or in a home office, filing cabinets are an essential component of an efficient workplace. They keep your paperwork tidy, organized, and out of sight, yet just a drawer away. And when you're short on space, they make a nifty counter for the coffee maker. Filing cabinets begin as sheets of cold roll steel, a thin type of metal that's easy to bend, weld, and paint. As the sheet comes off the roll, it goes through a straightening machine that removes the curve. Then into a press whose dies punch out the shape of the specific part, complete with holes, slots, and embossments. A filing cabinet is made up of 60+ steel parts. For the top-selling models, the factory has dies specially designed to punch out each part. But that's too costly a system for models that aren't mass-produced. So to make low-volume or custom-made filing cabinets, the factory uses this computer-controlled punching machine. This equipment operates at a far slower speed than the presses we just saw, but the advantage is that it can be programmed to punch out any size, shape, or design, no matter how complex. Several filing cabinet parts are designed to be bent into shape. Workers do that manually using a machine called a press brake. This particular part will become the top of the filing cabinet, so they're making downward folds along the perimeter to create 3.75 centimeter wide edges with strong and tight corner seams. This machine is called a dedicated bender because it's used to bend one type of part only, the filing cabinet doors. The factory produces doors in such volume that it pays to design a special machine to shape them. The doors, too, are bent downward along the perimeter to create edges 1 centimeter wide with tight corner seams. The cabinet's base is welded from the same type of steel sheeting as the other parts. Small steel reinforcements make it rigid enough to support the excessive weight of file-filled drawers. To join the cabinet's sides and back, robots perform what's called resistance welding, fusing metal using heat from an electric current. The next set of robots welds that side and back unit to the cabinet top. After this, workers attach the base using what's called MIG welding, welding that adds extra metal along the joint to create a strong seam. Once again, it doesn't pay to invest in robotic welding equipment for models that aren't mass-produced, so they manually weld low-volume items such as those small filing cabinets that roll under desks. In the paint department, rotary atomizers envelop the filing cabinets in a mist of paint that contains a synthetic resin for durability. These atomizers lace the paint particles with a negative electric charge. This draws the particles to a positive charge on the cabinets, creating a thorough and even coat. After 20 minutes in an oven to bake the paint, assembly can begin. Ball-bearing sliders on which the drawers will sit, tracks for the fold-down doors, and door stops so the doors can't be pulled off their tracks. There's also a locking system that simultaneously bolts both sides of each door, rendering the files inside inaccessible. The last step is to install the doors and drawers using a rubber mallet so as not to damage the finish. Each drawer can support up to 90 kilograms of files. An interlock system lets you open only one drawer at a time. This prevents the cabinet from toppling forward. A glass blower can transform a sizzling blob of molten glass into sheer sculpture, an object that's functional or decorative or both. Blown glass can be on the cutting edge of modern design, quite a feat for an art that's more than 2,000 years old. The first hollow glass objects date back to 1500 BC. The invention of the blowpipe around 30 BC revolutionized the craft. Until then, objects were either carved from solid glass blocks or molded from molten glass. The blowpipe enabled glassmakers to expand and shape glass, and it made fast, inexpensive production possible. This meant that everyday items, not just luxuries, could now be made of glass, accessible not just to the rich, but to ordinary people too. When you see these spectacular shapes and colors, it's hard to believe that blown glass comes from this bland, lumpy stuff. This is silica, a natural material derived from sand, mixed with thinners and stabilizers such as potassium and limestone. The glass blower recycles any leftover colorless glass, then loads the mix into the melting furnace. After 12 hours at fusion temperature, 1200 degrees Celsius, the raw material transforms into colorless liquid glass. The glass blower uses a blowpipe, a long steel tube with a ring or pear-shaped end, to collect what's called a gather, a glob of this red-hot molten material. To color the gather, she quickly rolls it in finely ground colored glass. At this stage, the glass is honey-like in consistency, though it's cooling and thickening by the second. She fuses the color layer by reheating the glass for a few seconds in a smaller furnace called a glory hole. Next, she rolls the glass against a ladle-shaped block to form a starting shape for blowing. A gentle blow or two bulges it into a hollow bubble. By now, the cooling glass has thickened to the consistency of caramel, making it more controllable and shapeable. The glass blower stretches and shapes the glass with different blocks and hand tools. The glass is like hardened caramel now and holds its final shape. She scores the glass where it meets the blowpipe, then cools it further with compressed air. On the opposite end of the glass, with a bit of hot glass, she attaches a solid metal maneuvering rod called a pontil. Then she applies a single drop of cold water on the score line to crack and break the glass off the blowpipe. Using another pontil, she plugs the resulting hole with hot glass. Then it's back to the melting furnace to attach a gather. It's critical to always rotate the glass so that it doesn't droop and become lopsided. The glass blower shapes this gather not with a block, but by hand. She protects herself from the intense heat by using a thick stack of soggy newspapers. Using an ordinary pair of scissors, she forms ridges. Then she twists the ridges to spiral them. She cools and hardens the finished design using compressed air. Then it's a quick blast in the glory hole to equalize the temperature throughout the piece. This blown glass lemon reamer has taken all of 8 minutes to make. Now it goes into an electric kiln for a slow 12-hour cool down to prevent cracking. Meanwhile, the glass blower starts a new piece, a large vase. more blowing, more shaping. Then, while her coworker blows air to further expand the glass and thin it out, she cools the vase's bottom with wet newspapers. This holds the cutoff point at the top. After reheating the glass to re-soften it, they stretch it, lengthening the vase. Once they finalize the shape, they use a wooden paddle to flatten the base. Now for some eye-catching decoration. Vivid colored glass coiled like taffy over the entire vase. Certain designs require cutting off a portion of the finished piece. That leaves a rough, opaque edge they must extensively grind and polish. A lemon reamer, a vase, even a mortar and pestle. A glass blower's work is clearly remarkable. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.